today there is an exhibition downstairs on the ground floor. All the department have a student doing a research except our department, but Mohammad will and other of his colleagues will make it very easy that we will have a poster in poster day. Thank you. Welcome.
All right. So first of all, I'd like to thank Dr. Mario for her introduction, and I also would like to thank the Pure Math Organizing Group, and also for applied mathematicians or physicists or even engineers who have come today. So let's start. Bismillah. So as the name suggests, we'll be talking about mathematics of mathematics, that is category theory. So this theory, we could say, is like a unifying framework for many diverse fields in mathematics, and we will see shortly what is it really about. All right, so here we got the meme, the application of category theory, world's first application of category theory, because category theory is known to be very theoretical, like barely you can see an application, even though it has some applications, but they may not be that obvious. All right, let's start now. All right, so first of all, I'd like to start with the question that what does it mean to truly know everything about something? So I'll start with very basic questions. These questions are philosophical in their nature. So what does it mean to know what a tree is? So the thing is that if I study a tree on its own, and I like to know many information about the tree, what do I know about the tree? For example, I know the color of the tree, I know the height of the tree, I know the day that I planted on it. Yet I don't know the number of the atoms that are contained in the tree. Neither how do the atoms are actually interacting with one another inside the tree. So that was an example. So we have, let's say, the standard model of elementary particles. You are now a particle physicist at CERN, and you are willing to study some particles. The thing is that you cannot, for example, if I want to study a specific particle, I cannot study it on its own. In order to study a particle, I have to study its interaction with other particles. So you get funded, you build an accelerator like the one in Switzerland, and then you collide it with other particles, and from these results you can obtain much information about these particles. All right, so the thing is that all information about an object is encoded in how it interacts with everything else. Let's return to the tree example. So I've said that we know the color of the tree, we know the height, we know some stuff about the tree. The things that we know about the tree are actually found by studying how it interacts with something in the nature. For example, we know the color of the tree because light will bounce off the leaves and then it will enter our eyes. And also about the height because you use a massive ruler, let's say, and then you would measure it. You know the day you planted them because you simply remember that day. Still, you are interacting with your brain in that sense. All right, so the thing is that here, in order to study an object, you have to study it in relationship with other things. You cannot study it in isolation. That's the thing. And this is called Uneda's lemma. It's a very fundamental lemma in category theory. And we won't be that rigorous while talking about that. It was just a simple introduction to this vast world. All right. So in mathematics, what I've just explained, it has become a philosophy. It has become a way of solving problems, a way of thinking. So let's say that you are now interested in studying the torus. It's like a donut shape. So in order to study, let's say, a seemingly complicated shape, what I do is that I draw continuous maps to the sphere, to plane, and other things that we already know in geometry. For example, I know how sphere is in geometry and also planes. But but let's say that the torus shape just popped out and I'm interested in studying it. The thing is that it is quite complex. So in order to study it, I have to find maps with the sphere and also with the plane. And this, I think, let's say, characterizes the idea of a manifold. For example, a manifold is something that's quite complex when you think about it. So in order to study that complex structure, what you do is that you find maps to more relevant shapes that you already know the structure of it. Yeah, so this is the idea behind it. So again, as I've said earlier, that you understand something not only by looking at it in isolation, but by understanding how it connects to everything else. So again, this was a way of thinking. Okay, so now let's see Uneda's lemma in action. You are now Galileo Galilei, you are in Italy right now, and you are interested in describing the motion of a bird that's flying in three dimensions. The thing is that if you have a bird that's flying 3 dimension, it's a quite complex thing to study actually. Flying 3 dimension, you know, birds moving there and there. So let's suppose right now it is in the morning, you have a sun that's being shaded. So in order to study the motion of the bird that's flying 3D, what we do is that we study simpler motions that what we can do is we can decompose the 3 dimensional motion of the bird into 2 simpler ones. The first one, we study the way the bird's shadow is moving on the plane, and the second one by studying how the bird's level is changing as it's ascending and descending, you know, the space. So basically what we are doing here is that we are studying the relationship of the bird's motion with the plane and with the line. And from these 2 motions that we have decomposed, we can reconstruct the bird's 3 dimensional motion. So what we did is that we have a complex thing, we have decomposed it into simpler things that we can study, and from that we can reconstruct it to be much more easier. And if you see this graph, hopefully we will return to it later on. This flag is related to the Cartesian product of 2 sets, or let's say like the product of topological spaces or groups. So this diagram will appear later on. So again, as I've said, and what I wanted to say is that what we are doing here is a philosophy of math. That's what is really happening. So again, as I've said earlier, Galileo noticed that complex motions are easier to understand when you are breaking it into simpler interacting parts, and we can really uniquely reconstruct. Please focus on the word uniquely. Uniqueness is very important. The bird's path. Similarly in mathematics, the nature of structures is revealed by the relationships, the maps they have with other structures. All right. Again, as I've said earlier, it does not apply to physical motion. It will the same pattern will appear in many different structures. Let's say even in mathematics, like product of topological spaces, logical conduction and proof theory, and many various things. So now, allow me to present the science of abstract nonsense. Yes, that's a nickname for category theory. Category theory. فبسم الرحمن الرحيم. Okay, who knows who is that mathematician? Okay, he is Alexander Grothendieck, a very famous algebraic, what was called algebraic geometry, and he said something about category theory, that if there is one thing in mathematics that fascinates me more than anything else, it is neither number or size, but always form, the structure, that pattern. And among the 1,001 faces whereby form chooses to reveal itself to us, the one that fascinates me more than any other and continues to fascinate me is the structure hidden in mathematical things. That's a very, let's say, important quote that he said. And all right, let's see what we got. Okay, so let's start again. So speaking naturally, what humans were actually doing since their existence, they were looking for patterns. They were interested in recognizing different patterns that are evolving, and also, as Galileo did, breaking complex problems into parts, solving them, recombining the results. A strategy that is seen from survival tasks to advanced mathematics. Yeah, indeed, that's, let's say, a human, that's an intrinsic thing in us. We are interested in finding patterns, and like mathematicians, we are interested in finding patterns. Then we realize perhaps it has no application. Then they will call us, oh, you barely do any applications. I quite often think that happens. So what category theory does is that it is trying to reveal deep similarities across different fields, like unified geometry, algebra, topology, even stuff in computer science, logic, and so on, through abstract structures. Yeah, so this is one of the goals of category theory. So it is trying to make a unified framework of mathematics, and secondly, it is, let's say, a way of thinking. Like when you think of an object, you think how is it related to different structures, rather than thinking of it on its own. So it suggests that we might be discovering, not inventing, some deep truths into the universe itself, like a kind of Platonic realm of mathematical reality. Some philosophy, we won't dive into that. Okay. So, as I've said in the introduction, why is category theory nicknamed the abstract nonsense? Perhaps I think you will understand that later on, but we have a short answer for that, is that let's compare it with different fields. That is set theory, and I think we have set theorists over here. So set theory, you know, well, you are studying sets, you are studying sets of objects, you are studying the internal structure more rather than category theory, where category theory emphasizes morphisms. We will get into that word later on. That are the maps and relationships between objects, enabling the study of structure that are hard to capture with sets alone. So rather than studying structure on their own, we are studying how are they related. Yeah, so that's, let's say, one of the things that category theory does. However, I think we haven't answered the question yet. Hopefully it will be clear by the end. So we have a quick historical background. Okay, so how did category theory started? So when did mathematics change? So category theory was born in the mid-20th century. I think during that time, or before that time, there were many fields that are popping up, let's say topology, functional analysis, and so on. And mathematics, let's say, had become some sort of separated. So we had two mathematicians, Samuel Eilenberg and Sanders Maclean. They formulated the notion of functional natural transformations. We won't cover natural transformation right now, but we will cover the notion of functors. And what they wanted to do is to simply organize algebraic topology. So initially it was a tool for topology, and it quickly proved usefulness in algebra and different other fields. Okay, so yeah. So as I said earlier, that mathematics has become some sort of very separated, and mathematicians were thinking of patterns, and we said that it is a very humanistic thing to do, is finding patterns and unify things. So people started working on category theory, and this was, let's say, the first start of category theory. So it started by algebraic topologists. The first time that I encountered category theory was while reading Hatchell's book on algebraic topology. So I thought that I should start doing a bit of category theory and get an idea or sense what's going on. Okay, so let's return back to Grothendieck. So he used category theory to reformulate algebraic geometry. Again, he was an algebraic geometrist. He introduced schemes and toposes. I think if you do algebraic geometry, you would understand these things. Laying the groundwork for the proof of Wales conjecture, which helped us in improving many important theorems. That's the Wales conjecture. So category theory, let's say, helps us into doing that. Okay, so now I'll be asking a question. What is category theory? Just a language? So if I ask you all what does a language mean? So a language is a set of vocabulary, a set of syntax and rules. You connect these words and then you establish a language. So is category theory just a language? Because so far as I was going, oh, it is just a unifying framework, you are just connecting things. There isn't that much that you can do with category theory. But before I dive into that, I will clarify what do I mean by that language. Okay, so we have different symbol systems or different languages, like Arabic and Roman numerals. So we have different numeral system. And if I ask you right now, which symbol system or which language would you prefer working on your computations? I think you would definitely say Arabic numerals. I don't think you would rather do math with Roman numerals because you would have to work C, M. So I don't think that's really convenient to do. So again, Arabic numerals are far more important, powerful, and efficient than others for expressing the same ideas. Same, let's say that we are returning back to 10,000 BC ago. We have so many different tribes. They have different languages. The language that will succeed is the language that's more efficient in expressing the ideas. That's just fact, a natural, what's called natural selection. You know, bad languages, they die. Good languages, they evolve. Or dominate, actually. Okay, so we are gonna, let's say, divide languages into two parts, non-compositional and compositional languages. So we have an example of non-compositional language that is called Piraha. I think it's in Brazil, in the Amazon. So what do I mean by compositional languages? So compositional language is that you can understand the meaning of the entire sentence by dividing it into small different parts, and then it is connected. So you understand the meaning of the whole by understanding the meaning of the tiny parts. However, in non-compositional languages, you can't do that. Even, let's say, if you start from simple beginnings, you cannot really form that many sentences like compositional languages. So yeah, the thing that compositional languages helps at expressing many different things. That's an advantage. So category theory is on the other end of the spectrum. It is a highly compositional language, often framework, and language as well, that will build complex structure from simple pieces. Again, as I said earlier, is that we decompose something that's very large into simpler parts, then I can recombine it to get many different results. All right. So again, in order to answer the question, category theory is not just a language. It can also be used to prove deep unifying theorems across mathematics. So the thing is that if you need to use it, then you have to be a very good category theorist. That's the thing, all right? But still, it can be used to prove theorems and many interesting things. All right. So now we will dive into choosing the right abstractions. So how do I know that I can choose let's say a valid abstraction? So let's return back to the example comparing the Arabic and Roman numerals. We said that the Arabic numerals are much more better than Roman one because if you see the structure and you see the pattern, let's say between 330, 300, even though they are just multiples of 10, let's say from 3 you can get 30, it's much more easier to manipulate and deal with these things. Rather than Roman numerals, you have C, you have M, you have XII. How am I supposed to do math with that? May God be with the teachers if they were teaching these things. So yeah, the thing is that good abstraction will let you discard relevant details. Like let's say if you are even writing code, this thing also happens in computer science. You are writing code, you don't want duplicated codes to appear. And also, what you want to see is same underlying pattern that occurs. That's the idea, or that's the goal for finding a good abstraction. And also, conceptual neighbors become apparent. So it will be much more easier and smooth to go from a different idea to another by finding a good abstraction, or if you have the good abstraction. And also generalize naturally, and you will handle corner cases like 0 factorial, 1 factorial. 0 factorial is it's 1, and that one is also 1, without breaking the original structure. That's also a very important thing. Okay, and abstract frameworks enable the idea plug and play, and it will let you connect disciplines without the need to know every internal detail. So that's the idea of plug and play. So you are just, let's say, again, if I have a good abstraction, I can just manipulate the things, play it over, but I don't need to know the internal structures behind it. I just need to know the connections and the pattern, just that. I don't need to know the internal structures. That's the thing about category theory. Some people say abstract nonsense because you are ignoring internal structures. I just care about the maps, or later on they will be called the morphisms. Okay. Yeah, and again, category theory, what we will see is choosing definitions let proofs becomes almost effortless, as we will see later on, and the structure itself carries the reasoning. So many proofs will just flow that way. So I think it's a very good thing to teach category theory because many proofs will just float away. You have just to teach it once, but the thing is that you'll be ignoring the internal structure. That's a disadvantage. Okay, so let's start now. Let's start now talking more technically about category theory. So we'll start with notion things, a set, again, naively speaking, collection of distinguishable elements. We define the Cartesian product over there. A relation is just a subset of the Cartesian product A cross A. And a function from S to T, it's going to be a relation such that each is mapped exactly to 1T. High school stuff. All right. So now we redefine pre-order. I think it was first introduced in 250, Foundation of Mathematics. So a pre-order is a set. You have a set of objects and you have a specific relation. It will satisfy two things, reflexivity and transitivity. And if S1 is less or equal to S2 and S2 is less or equal to S1, they are going to call isomorphic. And these are some examples of orders. You have the natural number and you can simply order the natural numbers. And again, it will satisfy these two things. Even the division 1 in number theory, if you are doing the number theory, it will still flow. All right. And also equality as well. And now if you are a graph theorist, again, a graph simply consists of vertices and paths. So we say that two vertices are related together if you can get from B to W, if you can find the direct path. And again, it will generate the same thing as a pre-order. All right. So now we discuss some important notions, the notion of top and bottom elements. The thing is that just ignore the word universal properties. We will come it later on. So a top element is simply, let's say if you are in a pre-order, you are ordering, let's say, a subset of the natural numbers. The top element is going to be the maximum number in that set. And the same thing with the bottom, but the thing is that it will become the minimum element. But these are, let's say, the more abstract concepts, or the more general forms. And again, we are going to reintroduce also the greatest lower bound, least upper bound. Again, just ignore the word numbers right now. So least upper bound, this is going to be the definition again. So you are expecting least upper bound of a subset of the set S. So it's going to be an element S such that for all S dash less or equal to S for each S dash. And if you have T that's greater or equal to S dash for all the S dash, then S is going to be less or equal to T. And the least upper bound, if you have just a set consisting of two things, is going to be called the joint. And also we can reverse everything else. We have the greatest lower bound, and the definition will just flow in the same form. And if you have just two elements, the greatest lower bound is going to be called the meat. Okay, so yeah, it would just to reintroduce these notions again. Okay, so now we'll be studying or talking about the maps of orders. Again, the central idea of category theory is that I would like to focus on structure preserving maps. So I have a map that would go from a set of order with the elements being ordered in that specific relation, and I wanted to map it to T with that specific relation as well. So again, this is going to be my function. However, since I want to preserve the structure that I had initially, this condition has to be flowed. That means if S1 is less equal to S2, we are currently in S. So the maps that will appear after that, I have to preserve the relation on the range of that function. So this is the idea of structure preserving, and hopefully it will appear later on. The thing is that I'm simply preserving the structure. Okay, and here are some examples. For example, we have inclusion. We have also the reciprocal. It will preserve these things. And sometimes the maps would preserve the joints. They may also preserve the meets and many different things. It may preserve the bottoms, tops. They are not necessarily. These are just examples for illustration. Nothing else. Okay. Rules of matrices. For example, again, I'm redefining the matrix. Simply, naively speaking, just a rectangular array of numbers. And addition, multiplication, these properties will follow on. Just simple 111 algebra. Okay. And again, the matrices need to be numbers, such that they will satisfy the property that we had earlier. The thing is that I can generalize it, so the entries could be from the ring. So a ring is a set that is equipped with two operations: addition, multiplication, and the addition has a natural element 0, and multiplication has a natural element 1, and should distribute over addition. And there are many examples I can choose. Let's say I can choose Z, I can choose N, I can even choose Z2, Z3, and so on. And I can also replace the operation like R. I can make the entries to be an R. The operation addition is going to be the maximum one. Multiplication is going to be the addition which is used in tropical algebra. So yeah, the simple answer is no. I can deal with it as wish, as long as I am satisfying the rules. Okay, so John Bayes, he was a guy who created the one of the most important nodes in category theory, and I think he's doing quantum theory, I think. I haven't got into that yet. So he was trying to explain to non-category theorists how do category theorists actually think. So he explained the concept of invergent category theory. So let's say you have a mathematician who's not category theorist and a category theorist. So a mathematician would ask, what's an example of this theorem? In ordinary mathematics courses, you have a theorem. The first question that would come to the student's mind is that what's the example of it? However, in category theory, we would ask, what is this example of? Like you are presenting something, and you are wondering, how could I generalize it? That's the question. So yeah, category theory, we are looking for patterns, and I think that question would answer that fact. So this again would reflect the category theory mindset. All right. So let us get into categories and actually define what categories are and see what they are really. So again, definition of a category consists of the following components. You have a collection of objects, And then you have for each of two objects, you could have something which is called morphisms. That is a set of arrows. You can think of it like functions. However, they are a more general concept than functions if you are dealing with sets. And each arrow is written in that way. And for each object, I have to have the identity arrow. It should be contained in the set of morphisms. And the composition rule must be satisfied. Like if you have an arrow that goes from C1 to C2, another one from C2 to C3, I have to compose these arrows. That thing should be satisfied. And these must satisfy the following axioms, unitality, and also associativity as well. For all the composable arrows F, G, and H. So this is category. You just have a bunch of things. Here, kind of, let's say in category theory, you are ignoring the internal details. So I just call them like dots. And we have the relationship between these dots. And they should satisfy associativity, unitality, composition rule, and so on, and identity. All right, so yeah, this was an example, this was the definition of a category. So again, we can think of categories the same way, like you can think of it as you are doing graph theory. You just have vertices that are objects, arrows that are the morphism between them, and this is, let's say, the usual thing that you would see in category theory textbooks or notes, in order to describe what a category is, like the simplest form. Okay, again, there are many examples of categories. So let's say that if I have a graph, I can construct a category which is called the FRG. So the objects are going to be the vertices, and the arrows are going to be the path connecting these vertices, and each vertex would have the identity arrow, and you can compose it very simply. This is often called the free category on G. Even though the intuition of categories thinking of it as graph, if you are doing graph theory, you can think of each graph as a category on its own. So yeah, don't get mixed between these two concepts. Okay. Also, I can view a set as a category. Like a set can be viewed as a category, which is called the discrete category. So the objects are going to just be the elements of S. And if I have two elements of S, I can draw these arrows or the morphism between them. Like if S was equal to itself, therefore I have the identity one. And if you have two distinct S, they may not necessarily be connected. And this is going to be the only compositions that are to be defined. Okay, so you can think of it as a graph. You barely have any arrows connecting the objects, just objects that are connecting on its own. So yeah, that's why it's called a discrete category. That's one of the reasons. Now I have a category set. So back then I wrote a set and I enforced it to be a category. Now I'm considering a category that consists of all, I have to be very careful with that one, of all sets in a chosen set theoretic universe, because I'm trying to avoid the paradoxes that would result as much as possible. We are avoiding paradoxes though. So all objects in U. And again, the arrows are going to be the functions between the sets. The usual one, identity will be there, composition. I think many things will just flow over. I just want to let you be exposed to many examples as much as possible. So as a graph, this is going to be very numerous. You have so many arrows that could be appearing from there and so on. So yeah, this is just the category set, just a category of sets, not set of all sets. And also order. Again, as we have introduced earlier, we have the order set, we have a set, and we have a specific relation. I can view it on its own as a category. So the objects are just going to be the elements of S, and the arrows, the way these elements are connected with one another, if they satisfy that condition. Therefore, I assign them a specific morphism. Otherwise, we won't assign them a specific arrow. And again, the rest would follow. Like each object would have identity arrow because S is less or equal to itself. Again, it's the reflexive one. And composition is going to work because of transitivity. So this construction is going to work because the axioms are just simplified. Okay. And also I can form like the same idea with sets, a category consisting of all possible order sets and a function that are going to be respecting the order. So the objects I have here are just orders, ordered sets, like sets, and each one of those has a specific relation. And the maps are going to be the order preserving map. That means this condition has to be satisfied, as I have introduced earlier. The IT-map is going to be automatically satisfied because it is automatically order preserving. Composition is also going to work. And again, even though it is really enormous, it is gonna neatly organize structure of order maps and maps that respect their order theoretic reasoning as well. Okay, so now I have a very interesting example about dimensions and matrices. So I have a category. The objects here are going to be the dimensions, and the dimensions, we know they are just natural numbers. You could have fraction of dimension, but we won't dive into that. Let's say you are doing linear algebra, you just have natural numbers as the objects. The morphisms here are going to be the matrices. This is, I think, the different example from the previous ones we had. So the objects are going to be the dimensions. The arrows are going to be the matrices. So the identity map is going to be the usual identity. The composition is going to be the matrix multiplication. So this is, I think, an idea that would generalize matrix multiplication. And later on, we will see where the addition is going to appear later on. So yeah, this is going to be this is our new beautiful category. So yeah, I think for me it is one of the most interesting categories that I've seen so far. All right. So again, it's going to package the algebra of matrix multiplication. So dimensions play the role of objects, and matrices are going to be the morphisms between them. Okay. So now we have another category of topological spaces. The objects are topological spaces. The arrows there are just going to be continuous ones. And the composite of two continuous maps is continuous. So you have composition, it's going to be associative, unital. The identity map is going to be certainly continuous. This was just, I think, a trivial example, even though topology is not trivial on its own. Okay, now we also have category vector spaces. Again, the objects are going to be the vector spaces, and the arrows are going to be the linear maps, because I'm interested in preserving the structure. So yeah, I'm interested more in linear maps in order to do that. Again, composition is going to be associative unital, composite is going to be linear. So vector spaces will be the objects, and linear maps will act as the arrow. So if anybody's interested in what's linear map, it should satisfy that condition. All right. Okay, so now I will do a bit of motivation into group theory. It will be just a small, tiny introduction, because I'll be introducing a quite interesting thing in category theory that's called a monoid. So let's say you are playing with the rubric cube, and you know, in order to reach to the most stable form, that is, on each side you have a specific color, what I have to do is just doing some transformations in order to reach to having each side having just a single color. So again, the action that we can perform of it, again, these are the specific actions that we do. So simply, we have a set of rotations. So we can view these transformations as a mathematical object, and that mathematical object is going to be the rubric's cubes group. And again, the elements are the legal cube transformation. I can flip that element into there and over there. And the operation is going to be the composition of moves. Like I do the first move, then I compose it to the next move. So yeah, this is going to be the operation. Element, I do nothing. I just leave the cube on its own. I don't transform. I don't move from a specific. I don't make a specific part move from a part to the other. And every transformation has an inverse. Simply, if I move, let's say, a specific part to that part, I do it again. This is the inverse, yani. So yeah, this is gonna be a group. Okay. However, right now I'm not really interested in a cube. I want to reinterpret it as a category. So let's create a new category. That category will consist of a single object. That single object is gonna represent the cube, and the transformations are gonna be the arrows, the morphisms into the cube itself. The composition again is gonna be the composition of cube moves. The identity is simply, again, the do nothing move, and the versus, they correspond to reversible transformations. So this gives, again, a one object category, and the arrows, they form a group. And if we remove the requirement that every arrow has to be invertible, so we discard the inverses of the morphisms, this new construction is going to use something that's called a monoid. Hence, monoid, we can say it arises naturally from thinking of operations on an object. I have a single object, I apply the arrows and make sure that the category theory laws are applied, so we get a monoid. Okay, so let's have a monoid. So let's define it. How is it defined usually? So a monoid is defined as a tuple. You have a set, you have an identity element for this binary operation that's defined in the same set. The operation is going to be associative, and it is going to be the unit again for that operation. So that's the definition of a monoid. This is not a category theory definition. However, now I can view it from a category theory viewpoint. So again, I have a single object. The morphism, the set of arrows are going to be the elements again, the transformation that we thought about it. So set of arrows are going to be the elements of the monoid here. The identity element is going to be E, composition is going to be just a star one, associativity, and these things will hold. Yeah, so this is the monoid. Yeah, I can't really say much more about it. So again, we have thought of monoid as a category on its own. We can relate monoids together, like what we have done earlier. We had a set, we recognize that as a single category. Then we define the set, the category of sets in a set theoretic universe, no paradoxes. The same thing we are doing here. We identify the category of monoids, so the objects are going to be the monoids. The morphisms are going to maps that respect the structure. If you notice that in the maps, what I'm interested in is structure preserving maps. That's what I'm interested in. And here we have monoid homomorphism, so it should satisfy these two conditions. I think these conditions we have seen in 261 for groups, I think so. So yeah, and mathematics again, this is what I'm trying to get you all to think, is that there are many patterns that are occurring. This is really interesting. Okay, so yeah, this was the monoids, the category of monoids. Okay, and we can not only we can also apply to different disciplines rather than think of it in mathematics. We can also apply to types and programs. So let's assume we have a category that's called P. The objects are going to be the types. The arrows are going to be what the programs that I'm doing here, the program that I'm writing the code in. So you know, in each program, I have, let's say, input and I have an output. That output could be a specific type, like bool, like true or false, integer, strings, and so on. So again, I can think of it as a category. The object is going to be the type. The morph are going to be the programs. Two programs I defined are, let's say, produce the same output when they are equal, I mean. And each type would have an identity program. If you have split input, it would just spit out the same output. Composition is going to be true because if you have another program, followed by another program, it will yield a program from A to C. And these are just simple examples, which I think you are all familiar with. All right. And there are also many different categories: groups, rings, fields, metric, measurable spaces, topologies, three-dimensional oriented Riemann manifolds, and so many things. So the new categories, they appear all the time because it would help mathematicians, let's say, they identify the pattern that occur in these different categories, so it will be much more easier to move from a category to the other. Because hopefully, I think soon we will introduce the notion of a functor. We will see what a functor is soon. Okay, but before moving to that, again, as I've said earlier, that if you have a category and the objects, you have a set of morphism between two objects. So again, so if you notice what I was saying a set of morphisms. A set, that means I have no additional structure, I just have a set of objects. So what am I going to do is that I will build, enrich it. So I will add extra structure to this set. Let's say if I have the matrices 1, if we return back to it and we add extra structure like the operation of addition and identify as a commutative monoid and we have an identity element, therefore we can deduce or reduce the addition operation that will appear for matrices, and also the left and right distributive flows, they will also appear. And this happens by enriching the set of morphisms, by adding extra structure into it. So again, it is naturally structured in commutative monoids. Not only is it applied to matrices, you can apply it for many different things. Because again, you just have a set of arrows, you add additional structure to it, and you get many interesting things like this example. I think there are plenty of examples regarding this one, but this I thought it would be the most obvious one to have. Okay. Okay, so returning back, we have defined the notions of top, bottom, meet, and join, and again, many mathematical objects are best described through the map that identify them. So if we return back to the start of the lecture, I have an object and I'd like to study it. Rather than thinking of it on its own, I think how is it related to everything else. Okay, so the notion that the greatest lower bound actually does, or exemplifies, it is called a universal property. So let's see what universal properties really actually are. So now we have something which is called initial and terminal objects. So the initial terminal objects, they generalize the idea of bottom and top elements. So again, top elements, you can simply think of it as the maximum element, as I've said earlier, of the set. and the bottom element is going to be the minimum element. So the initial terminal object is going to just generalize that concept. So we say that the object is initial if for every other object in that category you can find a unique arrow, and a terminal if we just reverse the arrow. So yeah, these are two definitions that would occur in category theory. So what we are doing here is finding a generalized notion. That would be, let's say, a unified thing that would work in many different categories, rather than thinking of the idea of bottom and top in a very specific category. What we are doing is just generalizing it, and that's what we are doing here. And there are some examples of where the idea of initial and terminal object they would occur. Okay, so again, as I have mentioned earlier, we have said I've told you to ignore universal property. We will be returning to it. So right now we are returning to universal property. So how did we derive the definition for terminal object, initial object? If you notice, the definition cares just about the relationship that we have to other objects. We don't care about internal structure. That's how category theories do. So in order to construct an object, what they do, for example, internal and initial object, they first of all think, how is that object related to everything else? And from that, we can get a new category theory definition or categorical definition. So these define objects purely by just their mapping behavior, not their internal structure. That is what I actually wanted to emphasize. And afterwards, I have to think it is going to be the unique best solution to a mapping problem. I have seen that if you have anything else that will satisfy the definition terminal object, it is going to be isomorphic to the initial and terminal object. That's what I mean by the unique best solution to the mapping problem. Okay, so before we're about to end, we are going to now generalize the idea of Cartesian product. Again, this is the unique definition of Cartesian product. And in order to generalize it to different structures, different categories, I redefine the Cartesian product in terms how is it defined by A and B, by the other objects, the relationships, to different objects. So we define the projections, the first projection to A, the second one is B, and then we would say that this is going to be the best solution to the mapping problem. Because if you have another object that will satisfy these properties, it's going to be isomorphic to that one. Hence, we deduce the general definition for the product, or the universal property of the product. And using this definition, you can write the product of two topological sets, two topological spaces, vector spaces, and many different things, just by using that formula. This is what I said, this is what I was mentioning earlier, that category theory is abstract nonsense, because you are just finding an abstract definition, and then you would just apply to different scenarios without caring about internal structure. That's the thing. We just apply them and you get many different things. You don't even know what's going on. That's why I think they don't really emphasize on teaching category theory. I think it should be taught like later on. So yeah, this was the idea of universal construction. And yeah, I said earlier it works in any category, sets, groups, function spaces. And if you notice, this diagram is even familiar to the diagram that we drew earlier regarding Galileo and the bird's flight motion. They are products at the end. This is quite interesting to think about. Okay, and now if we just reverse the arrows that you have seen in products, we also get the co-product. You just reverse the arrows and you get the notion of co-products. I think the examples for co-products are not that familiar to you. Like if you are a set, the co-product is going to be the disjoint union of sets, and opposite, like an ordered set, with a set with less than equal one is going to be the joint one. In matrices, is going to be the sum of dimensions. I think they are not as familiar as the example that we had about products. But for the sake of completeness, I've just included them. Okay, so before I move to functors, you can also apply or find a categorical definition for many things, like the quotient spaces as well, and many different objects. So if you are, let's say, taking course in group theory, you are interested in finding a quotient space for groups, rather than deriving things on their own and discussing the internal structure, you can simply ignore that and just apply the categorical definition. That's again why it's called abstract nonsense. Okay. So now I introduce the notion of functor. So a functor is going to be like a mapping between categories. So I've thought of categories on their own. Now I map the categories between them and get a functor. So again, a functor is going to preserve the structure. So the functor is going to preserve the objects. You just map them to the image of that object, even the arrows. So the functions are going to be composed with the functor one, and also identities, and also compositions. So yeah, functors are going to respect the structure. So again, it is going to preserve the structure of the category. So if you think about it, functor is like a morphism in the category of categories. Okay, but I think we'll get into problems with Russell paradox for the second time. Okay. And now I have just an example about function in homotopy theory. Don't ask me why I chose that one. Again, because I've encountered the idea of category theory while studying algebraic topology. So now I have homotopy theory. So what homotopy theory does is that it studies spaces up to continuous deformation. So we have a line, and these lines are said to be homotopic equivalent. So we can think of it as the same object since we can deform that one into that one. Think about like you are building as a string. Like if you have a string that, let's say that one, so you can deform it into that one. So we say that they are homotopic equivalent. So we have different functors. We have a functor that goes from topological spaces to the sets by mapping the space on the set of past connected components. We have also another functor that will map from the topological space to groups. And this one, or particularly the pi one, is called a fundamental group. So if you have a circle, let's say it is a topological space, and what's the fundamental group? So, how can I introduce that? Okay, so let's say, for example, you have a circle. Think of all the possible closed path that you can create. So in a circle, if you, let's say, draw a closed path, what you can do is that you can deform it and it just can be a point. So yeah, this is a fundamental, so any closed path is just going to be a point. So this is why I said it is zero. This is the sphere. Okay, often I was saying it was a circle. No, a circle, you are ignoring the interior. In a sphere, you are including the interior, and so these are the differences. So if you have a circle, you are ignoring the interior. So the loops that you can get is just the winding number that you can get, like how many times you are winding around that circle. So this is going to be the fundamental group. And I have a torus. So have included an image of torus. Okay, so a torus is like a donut, as we have seen earlier. So the loops are just going to be how many times I am moving around the hole that's appearing in the middle. So yeah, that's what torus is. So what functors do is that I'm mapping topological spaces into algebraic ones. So doing problems in algebra and returning back to topology, I think what it would do, it would make complex spaces much more easier to study. And that's the idea of functors, or the goal of functors. And at last, we are done. And this is the difference between mathematician and engineer and physicist. What mathematicians do, this is going to be subject. I don't like to get any information from it. Like I don't know the internal structure. I am just interested in the morphisms, regardless of engineers, mashallah, and physicists as well. So I hope this was an enjoyable talk. And thank you for all who attended today. So any questions?
Are there categories of functors?
Category of functors, the functions of their own. Therefore, I should map functors to functors. I think so. I think it would be. I don't quite know, but I think it is plausible. I think we can
do that nonsense, right?
It is going to be totally nonsense unless it's proven that we can have applications of it. Okay. تفضل.
I have a question that comes from physics, nothing to do with.
Hopefully,
and try to use the language that I can understand.
Okay, no worries.
You asked the question in the beginning. You said category theory is the point that we want to categorize something. How do I know exactly that in your definitions I'm not missing out on any parts? Like basically that your category this is the full definition of your category. Like you said, okay, the group is going to be this, the mapping is going to be that. How do I know this is the whole list that includes a definition of a category?
So, if I'm not understanding,
maybe
I hope I'm understanding right. So you mean like how can I make sure that if I'm studying something that is going to satisfy the category axioms, or why are category axioms written that way?
I mean, how do I know that all the axioms that you said that defines a category is sufficient to define this category, and there is nothing else missing. Like for example, let me say that there is a certain transformation that I'm missing somewhere. Mhm. Okay. I see. I see.
I think I doubt like they have thought of this. They define it like they abstract for many years. Then I think they have a definition which is hopefully sufficient for most cases. I think. I think that definition is gonna be
Sufficient.
this guy is gonna be sufficient. Yeah.
Thank you.
Thank you, Doctor.
Can I ask Mohammed?
تفضل دكتور.
You were saying at some point in your talk that using the language category theory, some of the proofs become very simple or become very trivial.
That's right.
Do you have an example of such a theorem that you
Example of a theorem, like right now I can't think of a specific theorem, but what we did is by showing that, let's say a theorem, I don't know if it's a theorem, let's say like the product of two spaces or of two groups. The thing that by simply using the categorical definition, we can deduce it really quickly, rather than doing rather than thinking of it in terms of its internal structure, we can quickly find the product of groups in that way. That's what came up to my mind right now. How I've answered your question.
thank you.
Okay, thank you.
Oh, this is a good talk. I wish all our students in fourth year and also master degree student will give us a talk sometime in their last year or in a master year. We are encouraging you to give a similar talk. This lets you to read more about the subject. So, what is great effort you put? Can you discuss to your to other students? How do you prepare for this talk?
So like if you are preparing a talk, what you are gonna do is that you will ignore many things. Like if you are studying something specifically, you have to ignore many things.